Hey everyone, welcome to the second video on large language models as retrieval and recommendation engines. In the previous video, first part of this series, we looked at basically what is retrieval and recommendation and search, and how we can use LLM as a retrieval and recommendation engine. If you haven't watched that video, please go ahead and do so. We go into a lot of details there about these topics. But today we will look at basically how we can make a small demo using vLLM library and how we can basically benefit from that constraint generation mentioned in the previous video and build that retrieval or recommendation engine. And we will also look at the code. I will share with you the Colab link, the Google Colab notebook. And with that being said, let's just start the video. We have the part one of basically this video and the blog post where we talked about the LLM recommendations. But today we will start by talking about the vLLM library. It's actually, I would say, quite famous right now in the community of machine learning, especially in large language models. The LLM is in the name. So it's a very useful library when you want to have fast and scalable systems for serving LLMs. And it allows for different things. Like, most important thing we're going to use it for is the constraint, or as the vLLM calls it, guided generation. It also allows different things, if you want to make things like streaming available for your LLMs, that's also possible using this library. But in short, it's pretty useful, and you're gonna see how we can use it for making a recommendation system. Okay, so to begin with, we can talk about the constraint decoding with vLLM. Constraint or guided decoding, basically, with vLLM, the way it works is we define a kind of a schema. So it's somewhat similar to how we would do a JSON mode or like a structured output with OpenAI as well. So all these libraries have a type of similar implementations of this. Like OpenAI library has a structured outputs or JSON mode. I think it used to be called JSON mode, now it's structured outputs. The LLM has its own thing, and Hugging Face has its own thing. But basically, you define a schema. You would say, hey, if my LLM is going to output something, I just want it to be a certain schema. Like, for instance, for us, let's imagine we want to do movie recommendations. So I want to say whatever the LLM is outputting, I want it to have a title. And let's say I wanted to have, for example, date when it was published or other things like that. So you can define a kind of a schema structure that LLM has to follow. But for the sake of simplicity, today we just stick with a list of titles rather than objects of different parts, like title, date, and all that. And the way things work is it uses a system called finite state machines. I think people from computer science or computer engineering background or other engineering backgrounds actually might be familiar with it. It's not a really complicated concept, at least to the extent that we will talk about today. It's actually pretty simple. It's just that you can basically move between different states. And at each state, you can better stay there, go back, or go to another state. And the way we will do constraint generation using these FSM machines is that when the LLM starts outputting tokens, let's imagine this is the first step, this is the start, which is also similar to the idea of the tree that we talked about in the previous video. It's similar to that try tree that we mentioned. So that's the start token. Then from there, you can go to some other tokens. It might be millions of options here, literally millions. And each one of these is another state in a way. And LLM basically based on what's the most probable first token will decide what state to go on. And what this machine does is basically limiting the LLM. So when the LLM is limited, it cannot go anywhere that it wants. It has to go somewhere that we allow it to. So similar to the idea of try-tree we discussed. So here, let's imagine we want it to output a movie name called, let's say, The Lord of the Rings, for instance. So the LLM has to start with D. Let's imagine each word is a token, which in reality it's not, but let's imagine here. So there's like all these other options that the LLM could have taken, it didn't. And the next one the LLM wants to go to will be the Lord, right? And if you haven't watched the first video here, you may be like thinking, why does it matter? Like the LLM ChatGPT, I just go and ask it for a movie, it can say The Lord of the Rings. The reason it matters is like sometimes the small LLMs especially start hallucinating, as we discussed before as well. And this hallucination may like end up generating something like the Lords of the Rings, or the Lords of the Ring rather than the Lord of the Rings. So it's subtle, you may not even notice it at the first, but nevertheless it's a mistake. So this machine basically makes sure when the LLM is generating the next token, the token is the Lord, or the word is the Lord, rather than Lords, or like some other basically close but not exactly that, or even something made up. Instead of the Lords of the Rings, you would say the Kings of the Rings or something like that, which doesn't even exist. And so the LLM can better select from the Lords or like some other options. But here, if your LLM have enough world knowledge or has received enough training, if a small LLM received enough fine-tuning, it will correctly select the Lord of the Rings based on the user history. If LLM thinks that user will like Lord of the Rings, it starts outputting basically tokens ending up creating the Lord of the Rings. So here, then again, from that token, it can go to different states. Anyways, the idea is not too complicated. It just basically limits the LLM at each step to certain tokens that it can take. Coming back here, so that's basically what happens behind the scenes. I just wanted to quickly talk about it. And in regular LLMs, basically any token is possible to go to, while in like LLM that's like limited by finite state machine, only certain tokens are possible, and you usually have a vocabulary of 30k to 100k possible tokens. And with limiting this, you can go as little or as many as you want again. And the idea is like, yeah, from here only these next tokens are available. And if you imagine like LLM is a train going on certain tracks, this finite state machine or this like constraint generation basically at every like intersection between the rails, it allows it to take a certain rail rather than just going off rail, going into the weeds or something like that. So it just allows it to move, but on certain directions. If you imagine it's a train, then it can take only the directions that the rails exist on. Okay, so enough talking about the background, and here I'll remind you again, if you like to hear more about how all these things work, how this whole idea of constraint generation, LLMs and recommendation, how to fine-tune, please watch the previous video. I'll go to the details there. And here we can start by looking at the code. And this is also available as a Google Colab notebook, which I made available at the end of this blog post. But here there's like code snippets of it. So for the sake of simplicity, I'll stay on this window. You can have a quick look at the end of the video at the actual Colab notebook and how to run it. But for now, I'll just continue from here. Okay, so basically, as you can see, the top part is just imports, nothing like too complicated. We need a few specific libraries, like Pydantic will help us for the structured output thing we talked about. And basically we have vLLM, which will be the library that will help us serve LLMs. And vLLM, again, super famous, and I've seen it in a bunch of industry applications, and I personally use it in a lot of cases. So it's definitely something worth learning about if you're serious about becoming a machine learning engineer in the era of these LLMs. And there's like we can like sort importing things from the sampling parameters, like guided decoding prompts. This is like something that will help us again with the structured output thing. And you can select basically any model from Hugging Face, anything there, as long as you can basically safely host it. I mean, if you have enough memory to host it, you will be okay to basically put here. It's just any model ID from Hugging Face. For the sake of simplicity, I'm just using some 4 billion Quen model, but select any model. Of course, if you're learning it on Google Colab, then likely you have to stay with something like 4, maybe 8 billion parameter model will run on Colab, but I would say probably not, unfortunately. And here we just we just give it the name of the model we want to run, and then this D-type half thing is just determining the precision on floating points on the model weights, and it's not super important, but certain certain backends for these libraries sometimes don't allow anything except half, so you can just leave it on half for now. And max model len is basically the maximum length of the output that we're allowing this model to have. I'm just putting it on 500. You can put it on more tokens if you want longer outputs. If you want fewer, shorter outputs, you can put it on fewer tokens. And here the interesting part starts. We want to, as I mentioned, we want to keep it to a movie recommendation application. So we start by defining our kind of corpus, or kind of our catalog. It can be a lot of items, or it can be a few. Here, for the sake of the demo, I just defined about 10 items here, which a lot of famous movies here you can see, and some of them are absolutely unrelated. There is cooking with tofu, and there is history of quantum physics. There is I actually intentionally tried it to be a mix of different things. So, but here is the movie parts. Yeah, here it starts about cooking, and then some random stuff there as well. So we basically define the structure of our output like this. Right now we define a literal, and we just said, hey, this should be from the allowed item. So this basically limits the LLM to only output from this option. Okay. So this is the important kind of part of all of it, is that this items structure now limits the LLM to this defined kind of set that we have here, and the LLM will only be able to select from here. So this is somewhat also different from that JSON mode, or the structure that you can define. So we have, as I mentioned, we can define, hey, right now we are only defining the structure to be a list, but saying a list of these items, right? But you can also define it as a different thing. You can define it as a list of dictionaries. You can define it as a list of different objects. Each object, for example, instead of just saying, hey, titles, maybe each movie would have had, say, title, release date, duration, all that. That is all possible, but I just kept it simple here. But if you look into vLLM documents, or more codes on the internet, you can easily find examples of that. And continuing on this here, we make a class. This class is basically also saying, hey, this is our output class. It's a Pydantic class, and basically the only thing inside it is these items. This is a different items from these items. This is saying, hey, this is a list of items which we defined up here as a list of these potential movie or videos. And these items is like just the attribute in this class. So you can even name something different here, whatever you want. Like you can call it videos or whatever you think would work best. And but important part is we define the structure. We define the structure using Pydantic, and we limit the options by a literal and defining a list. That's the important part here. And the schema is defined. We pass it to these sampling parameters or sampling params here. And temperature is like basically quick. TLDR is like it allows how much randomness, or like some people call it creativity, the LLM would have in its output. I usually put it on 0 for cases where like the output is kind of structured, output is kind of limited, because I just want it to be selected from what I have. The more you increase the temperature, the less likely actually it is. The model sometimes doesn't even stay with the structure you define. So I would suggest for cases where you're using constraint generation, just stay with temperature of 0. Well, otherwise a temperature of 1 is usually something like a default. Again, you can define maximum tokens here. I just put it on 50. If you want more outputs out of LLM, increase it. And then guided decoding, we're passing that schema we define. And repetition penalty is also something interesting here. Sometimes it's small LLMs or small language models, SLMs, they tend to repeat certain options too many times. And it's because, well, they're not as intelligent as, say, something as big as ChatGPT. You may not see ChatGPT constantly repeating itself, but if you look at like smaller models, they occasionally do. So this repetition penalty basically penalizes the model to not output the tokens it already has. It is good in our applications. I would say it's pretty useful because sometimes, especially like in our example, the items are quite different from each other. And it definitely helps, but sometimes if your items are too close or too similar, it may negatively impact it. This is something to tune. Maybe a value of 1 would work instead of 2 for you as well, or even 0.5, or you may not even need it. But that's definitely something you need to experiment with. But for here, I'm just setting it on 2. And okay, so kind of everything is just set up here. We defined our list of possible items, and we made a schema. We passed that schema to sampling param. So now we have like a kind of a way to tell the LLM how to sample from the tokens. And all we need to do is basically now give it a prompt. The prompt can be kind of simple or complex. So like for sake of simplicity here, I'm just saying, hey, recommend me a good fantasy adventure movie. And the output of the LLM is like Harry Potter, Lord of the Rings. And if we go back to what we had here, we had a bunch of random stuff, right? We had cooking with tofu, we had how to bake croissants, we had like making pastries at home, all that stuff, history of quantum physics. But as you see, the LLM correctly stays with like the 2 fantasy adventure movies. And how could we make this even better? The way we could have like made this even better would be like, hey, you have your prompt, and your prompt is basically a part of it will be your user profile, right? And then the next part would be the instructions, which would say, hey, recommend me this or that. But user profile would give the LLM a lot of ideas about what to show to this user. Like for me, for instance, would be like, hey, this user has watched Lord of the Rings, has watched the Batman movie, like the Witcher video games or something like that. And then LLM will start thinking, okay, this guy likes fantasy. And whether it's video games, whether it's movies, TV series. And then if you had a million different type of movies to select from, a million different titles of movies, it would start suggesting adventure movies to me, right? But here we don't have that for, again, simplicity, but you can start adding a lot of things to the prompt, like previous purchases, previous clicks, previous like watches, how much each user watched what video, and then ask the LLM to like output something. And your LLM can be whether a fine-tuned model or like a large commercial model like GPT. That's where the best results come out. And then LLM would output basically movies. Okay. But here, as I said, we don't have it, but potentially you could enhance the prompt with user purchase history or things like that. And yeah, I guess we kind of are getting close to the end of this video. But we saw how basically you can easily make a recommendation model. We made a very simple one. I encourage you to try different things, try the prompt, change it, and try to see how each model works, like by, hey, if I give enough information about user, will it make the predictions better? Try changing these options here I showed you. Maybe try with like different musics and like give you some of your own past music taste and see how it recommends you new music. And what's beautiful about this is like, hey, traditionally we used to think about recommender models as something like, hey, matrix factorization or like tree-based models trained on a binary way. A lot of like complicated things used to go into this, but these days you just need an LLM to like make a good recommendation model, and they often even have the possibility to outperform the traditional models. I had linked some papers in the previous blog post and the video that showed, hey, this LLM method can even work as well or better than the traditional models. So this is just a recommendation system and very easy to use. And maybe if you have like trying like a small website, or if you have the possibility to like host LLMs, that is, of course, I know it can be costly. You just have a recommendation model to start with. And there's a link here. Sorry, there is like some sort of box here. I don't know what is this large box here, but if you click on the link in the whether description of the video or the blog post, it will take you to this Colab notebook. The only thing I wanted to just mention about this notebook is like I have specifically set the value on the basically the versioning of these libraries to a certain number, to a certain version. The reason is because I know with this version, this syntax that I have will work correctly, but maybe in future updates the syntax will change. But otherwise, you can try the latest versions, but I think the vLLM 0901 is not too old. It should be only like a 1 or 2 months old version or something. And feel free to try the new ones, see if the syntax still works, but I'm just keeping it at this for now. And same code I showed you here, you can just try running this block by block, see the output, and here basically start changing like start changing the options and see like what happens and experiment with it. And yeah, and you can try even like changing this repetition penalties, see what happens. Okay, with that we bring the video to an end, and I hope you enjoyed watching this. And if you haven't subscribed already, please consider doing so. I will be putting out more videos similar to these. And check out the description for the link to the blog posts and the first part of this video series. And thanks for watching, and I hope to see you in the next video.